Hi, welcome to this episode in which we will be talking about our first lively vectors function, which is called LV clean segmented. In this episode, we will be analyzing this publicly available brain computer interface dataset. We will start this with cleaning function, and we will be assuming that this data is not filtered. There was actually some filtering applied to this data, but we are going to assume that there is none. So we can press Ctrl D and open this function. And what I will do, I would like not just to talk about the function, I would like to debug this function. So we are going to go through the code step by step together and see what is happening with this function. So first of all, we can notice that, as we said last time, that we have created this struct. It's including trial and then channel and then time dimensions. And we are describing each one of them like time, label, and samples. So right now I'm passing this to my function. So that's the first thing, the struct. And then I'm passing the beginning and end of the time period, and I'm going to use this as my time of interest. So basically I'm calling this the stats window. So I'm going to use all the time from 0 seconds to 4 seconds to do my statistics, to calculate any statistical analysis that we are gonna use to reject or clean our data. So and I'm going also to pass like an index for the participant that we are dealing with. And then we can open this function. I can just press F3 to step into this line. So right now we are inside the function. So the first thing that we do in this function, I check this my struct if there is any layout. So we can create a layout for our data, which is the topography or the position of its channels and how they look like. And also we can use this later in other analysis, as we will see. So we can do that, and also we can load an existing layout if we have created something. And I actually, most of the time, I see which channels are included in my data that I collected or I have online, and then I load a pre-existing layout. So for instance, if we step into another function, we can load a layout like this layout, which is built in FieldTrip, and then we can extract this layout and then match the channels and see which channels we have in our data, and just take the locations and like any specs of this of these channels from the existing layout, and we will treat this as our new layout. So here we have 12 channels. We didn't specify the layout, so it's gonna jump to else, and it's gonna load this layout that I have created with this part, and then it's gonna define what we call the area of interest. So basically these are the 12 channels, but this wouldn't make any difference because we have already chosen these 12 channels before. So here you can put any area of interest. So let's say that you are interested in 3 channels, so you can put them here, and they are going to be effective later on, because using this area of interest I have put some constraints, such that if there is any trial that has more than 25 of channels on this area of interest to be noise, to be outliers, this trial is going to be rejected. So that's how I'm using the area of interest in this code. So we can define this threshold of 0.25, and then here I'm just like getting the index of these channels, but inside the labels. So that's what this function is going to do. So now we have the indices, and of course they match because, as we said, we have chosen these channels already. So after doing that, I'm here checking the dimensions of my data. So basically we can open this one and see if our data is in the golden tensor format, which means that we have trials and then channels and then time. If so, then the size of the data will have 3 dimensions and the length of this will be 3. So here I'm just checking if we have our data in this format. If it is not in 3D format, I'm going to change it using this time look analysis from FieldTrip. And what this will do, it will put our data in the 3D format. I also have a lively vector function to do this, but this is achieving the exact same functionality. So instead of having trials as a struct, we have it as one one tensor like that, including all of our dimensions. So right now I'm just copying this inside data and just displaying that this is like the part for rejecting outliers. And the thing is, you can do this in a way if you are certain that your data is normal to some extent, then you can do this as rejecting trials if they are 2 standard deviation away from the mean. So what I mean by that, let's say that we have our data to include one value and we have a distribution. We create a distribution for our data, and our data more or less looks like a bell curve, looks like a Gaussian distribution like that, so that we can define our mean very clearly, and then we can look at a standard deviation, 1 standard deviation away from the mean. We can look even 2 standard deviation away from the mean, and we can define anything that will fall in this part as an outlier. So we can later on reject this and say that this is an outlier and I'm going to reject anything falling in this area. And we can do the same in this part and define our 2 standard deviation away that are lower than the mean, and then reject any trial or any signal or any sample, whatever we are doing, that fall in this area. This is of course if you are certain that your data is normal. So what will happen if you are not certain about this? We can then think about other things to do. So we can think about using the median to get the interquartile range, and that's exactly what I'm doing in this code. So I'm here not assuming normality of the data, I'm just using the interquartile range, and we are gonna see how this is done in a moment. So in this part I'm just um, reducing my time dimension to the time of interest. So basically, as we said, this is the stats window that we have specified from 0 to 4 seconds, and then we put this as our latency, and we pass it to a FieldTrip function to select the data. So it's gonna reduce this time dimension if we have a smaller region of interest or time of interest. So what happens is, this is now the new data. It should be reduced, but of course, because we are choosing the same time points as the ones we have inside the struct, so it is not doing anything here. And then here I'm just making sure to lower this, to have them in a lower case. That's better for comparison later on, and also changing the data.label to be the same, to be just a lower case of the labels. So just turning every character into lowercase. Okay, so now to this part where we start to do actual statistical analysis, and we are gonna use our data to trial. So that's our golden tensor. So it's gonna be handy to look at the golden tensor and imagine what is happening here, because what we are doing here is basically we are taking the variance. We are taking the variance in the third dimension. So the third parameter here is the dimension, as we see. So the second one is the weight, so I'm not gonna put any weighting. So the third one is the time, so we are calculating the variance in the time dimension. So what the variance is actually doing is something that looks like that. So we basically have, let's say, our signal looking like that, and we have to calculate the variance. So we can imagine that this is like the mean of all the data points, and if we are centering our data, this will be of zero mean. So we are basically subtracting the mean from all samples, and what happens is if we are going to calculate the variance can be described as how further away the data points are from the mean. So basically, if we have data like this, and if we said that this is like an average variance, so this is not a huge variance. If we imagine that we have another data like that, and the data is going like crazy like that, and it's really increasing and decreasing very huge like that with huge amplitude, this will have a very high uh, distance from the mean. So basically, if this is the mean of our data, then the distance from the mean of each from each sample is high. So actually, the variance can be described as if you take every sample and you subtract the mean from that sample, and you repeat this for all of your samples, and then you square that, because we don't care about the direction whether it's positive or negative, and then we sum all of this, and then we just normalize by n-1. Um, so it can be described as x, where x is every sample that we have, x minus, let's say, mu, which is the mean of our data, and this is divided by n minus 1. You will see different normalizations, but this one is the one I'm describing here. So it's more or less something like this. So we take every sample, we subtract the mean from that sample, we repeat this for all samples, and then we sum all of this, and we square this before we sum. So we take the difference, we square this, and then we sum this for all samples, and then we divide by n minus 1, where n is the number of samples. So if we have 100 samples here, this will be our n, so we'll be dividing by 99. Okay, so that's a basic idea about the variance. The mean is just the average of data. The minimum and maximum would be the minimum and maximum values. So this value is the maximum, and let's say this value is the minimum, and so on. So this is very handy, because we can imagine if in our data we find something that has very huge variance, that's something suspicious, such that it makes you think whether this is a normal variance or is it an outlier. And also, when we check the minimum and the maximum, we will have a rough idea about the minimum and maximum that are normally happening in our data, and what kind of minimum and maximum are really huge or are very small, such that they should be outliers. And the mean is the same story. If the mean is quite different, like all the trials having zero mean, and just one of them is like having, I don't know, minus 2000 or something, then this is clearly an outlier. So I'm doing all of these measurements in the third dimension, which means that we are looking at this in time. So basically we are doing this in time. So we can look at our golden tensor and imagine this in a second. So looking at our golden tensor again, we see that we have the three dimensions, trial, channel, time. We said that we are going to act on the third dimension, which is time. So what we are doing here, we are getting the variance across time, across the third dimension. So we can imagine that when you get the variance, you're going to end up, instead of just having a signal, you will have one value. So it's more or less like compressing this third dimension. It's something like that. So you are compressing this third dimension, now you wouldn't have time points and you will end up with trial channel dimension and just one value representing the mean or the variance or minimum or maximum. Okay, going back again to the code, we can see that when we do that, we have three dimensions. When we get that, we'll have trial channel, and then the time dimension will be 1. So it will be 1. That's why I'm doing this. So I'm using this squeeze function in Matlab to squeeze this singular dimension, which is time, such that we just have trial and the channel dimension as we see. So now 200 trials by 12 channels, and that will be the same case for all of these measures. All of them will have the same dimensions. Okay, going on to see the interquartile range. Here I'm just initializing this matrix. I'm calling this matrix good flags matrix, and this basically has a boolean value, so it's either 0 or 1. So basically I'm just initializing this with nan, and then I'm looping over the second dimension. So I'm doing this for every channel. So we can imagine that if we have our data like that, now that we have trial and then a channel dimension, it will be like so. That's a trial and that's a channel. Now I'm looping on the second dimension, so I'm looping at every column like that, and I'm doing my stats. So I'm basically extracting data from every column, and then I'm gonna do like a distribution of these different data points inside of here, and then I'm gonna see the 25 percentile of data, and then I'm gonna check the 75 percentile of data. So then I'm gonna see, of course, the median is the 50 percentile of data. So what we're going to do here, we're going to extract the interquartile range. The interquartile range is defined as this range from the third to the first quantile, and then I'm gonna get this and define it as IQR, and then a value that is an outlier is defined as anything that goes below the first quartile minus 1.5 multiplied by this interquartile range. Okay, and people normally play with this value, so you can see that this could be 3, this could be 2 and other things, but I mean, I think in a lot of places you'll find this 1.5, and this will define any outlier going very low, lower than the median, and anything going very high compared to the median, going higher than the median will be 1.5 multiplied by the interquartile range, and all of that is Q3. So that's Q3 plus the 1.5, the interquartile range. So of course this is not pretty, so let's look at the code and see how this is defined. So as we said, we are going to loop on the second dimension on every channel and do this. So luckily in Matlab we have this function, so we can immediately get the column of our data and then calculate the interquartile range. So we are going to have the interquartile range value. We can also calculate the percentile, so we are going to calculate 25 percentile and 75 percentile of our data, such that we have these values. We are now able to do our thresholding and take this as a two-sided threshold, so basically locating anything going very low compared to the median and anything very high compared to the median. So Q1 minus 1.5, the interquartile range, something that is going very low, something that goes very high, Q3 plus 1.5, the interquartile range, and that would be our threshold, the low threshold and the high threshold for the variance for our first measure. and anything that goes below this value of -7 will be an outlier and should be rejected, and anything going higher than this value should be rejected as being very high. I'm repeating this for all other measures, so for the minimum and for the maximum and for the mean. And then what I'm doing here, I am just putting all of them together. So basically this is looping on the columns of our matrix. So this matrix, here we are on in the first column, and here we are checking whether our value is between the first, it's higher than the low threshold and lower than the high threshold, then it will be a good value. And in the meantime, it's like that. So just why I'm putting this and, it's like that for all the measures, for the minimum, maximum, and mean and variance. So basically, after we execute this, we're going to see ones and zeros in this part. So some of them will be good, and some trials will be bad on this particular channel, such that we can imagine when we do this for a second and third iteration and we loop on all the channels like that, we're going to end up with 1 and zeros matrix defining the good trials. Right now, if we look at this, we have trials and channels. So for instance, this trial is very good because it's good on all of our channels. Let's see, one of the trials is like that, it's very bad. So this is an outlier because this is going further away from our median in all of the channels. So here I'm doing something else. I'm looking at the outliers and the number of outliers. So here I'm doing like checking the area of interest again, the index of the channels, and I'm taking anything that is not good on this area, and I'm comparing this to the length of the area of interest multiplied by the threshold of 0.25. So basically I'm seeing that do we have a number of outliers more than 25% of the total number of channels, which is 12. So we take 25% of that. Do we have more channels than that that are having zeros? If that's the case, then this is gonna be a bad trial. So here I define the trial is bad on the area of interest, so it's gonna give me a number of trials with a flag, ones and zeros again, and then I'm just putting in the good flags matrix again, I'm putting anything that is bad on this area of interest. So I'm accessing the trials dimension, and anything defined as bad, it's gonna be all zeros, and this is gonna be important for the other steps. So we found that we have 27 trials rejected for being bad on the area of interest, and then we can see that we see the perfect trials. We can see the perfect trials. So basically, if you sum this and this sums to the size, this sums to 12, then this is a perfect trial. So it's a trial that doesn't have any bad channels. So we have a lot of perfect trials, and then we can find all good trials. So here what I'm doing is that I'm taking the summation in the second dimension, so the number of channels again, dividing this by the number of channels to get this as a percentage. So I'm just calculating the percentage of good of trials being good on how many channels, and I'm defining the threshold. It was 25%. I'm taking 1 minus such that it's 75, because that's defining the good, not the bad. So if a trial is having more than or equal to 75% of its channels as ones, so defined as good, this is going to be a good trial. And then I'm saving this inside all good trials, and then just defining a set of indices as bad trials. I'm putting all the indices as bad in the beginning, and then I'm clearing out the good indices that we found here, such that we just end up with some trials defined as bad. So right now we have from our trials we have almost 87 trials accepted, 87% trials accepted, and then we can see, like here I'm just putting the stats for reference. So all the stats here include all the stats, and yeah, I'm gonna use this for plotting later on. But anyway, after doing this step, we have the indices of good trials, perfect trials, and some of the bad trials as well. So what I want to do right now, any trial that has less than 25% of its channels defined as bad, I'm gonna interpolate these channels using the values of the neighboring channels. So basically, if we have a topography, and this topography looks like that, so we have the nose and the ears like so, and we have a lot of electrodes like that. We can imagine that if we find this channel to be bad, so if this is a bad channel, we are going to use data to, are gonna like remove the data from this channel. I'm gonna interpolate the data using different channels near this channel. So I'm gonna use the data, let's say from this and this and this and this, all of these channels. I'm gonna get the average of them, and I'm gonna assume that this is the values of the data we get on this channel. So that's more or less the idea. Of course, here it's more like not really a data-driven way of getting the values. So we don't care what is the data looks like on this channel or this channel when we are calculating this one. It's more about the distance. So of course we care about the data, but it's more about the distance from the bed channel that needs to be interpolated. And here in FieldTrip, I have specified the method as triangulation. Triangulation is a nice method. I think in this one you can check this on FieldTrip website, but I think just for simplicity they are using a lot of triangles until they cover the whole area of nodes or sensors, and then they are locating the neighbors for every channel. So we can see that if we go over this one, we can see neighbors, and for every channel a lot of neighbors are defined that are located near this electrode, and this is happening for all of our channels. Okay, so in this section, what we are going to do, we are going to have our data, and we're going to interpolate the bad trials. We're going to interpolate the trials that are good for interpolation and they are not completely outliers. So they have less than 25% of channels as being bad. So I'm gonna interpolate these channels. Here I'm including two versions. So the second version that I commented on this part is like a brute force solution where I'm looping on all trials basically. So I'm creating a very huge loop on every trial, and for every trial I'm defining like the channels that are bad, and then calculating the weights for interpolating this channel, and then doing the actual interpolation. The problem with this is that having a lot of search areas, so basically I'm looping on everything, on all trials. So in this one I'm trying to reduce this. I'm trying to make this in a nicer way. So basically, because this is dependent on the distance, like if we have 10 trials having the same bad channels, all of them will be interpolated in the same manner. So that's why I'm using this function unique to get on the rows dimension like which one of them are unique, and then I'm seeking the indices of those, and then comparing those indices such that I just look at the trials that are similar to each other in the same iteration, and instead of looping on all trials. So basically, if we do this many times, let's say here index, so this is one trial, perhaps we can find things that will do for more than that later on. And this tick and then tock will just calculate the time if you are interested in this, and then it's going to interpolate for 1, 2 trials and so on. And inside of this, I'm just here doing a check, because this sometimes when it comes back from the function, it changes the order of the labels. So here I'm just matching the labels that are coming from here with the labels in my struct again. I'm having this in a new index and then putting the interpolated data inside of our struct again. So now we have our data and it should be interpolated, and then I'm putting this data interpolated in a final data interpolation, and then I'm here having this function that you cannot check, but here I'm simply accessing some random trials, some perfect trials, and some good trials, and some bad trials, getting some like some random trials and just plotting them and calculating the variance minimum and maximum for them. And you can see that it's gonna look something like that. So you are gonna have some perfect trials, these are the bad trials, and that's good trials, and that's perfect trials, and you can look and visually inspect some of them. And then here I'm just doing a check to see that the trials actually match with the number of trials that we have originally, and then that's everything in this function, and then we have returned again to our main function. Okay, so next time we are gonna see more cleaning, actually more of manual cleaning, and I have to say it's very good to do a lot of pre-processing according to what kind of analysis or what kind of task or activity you are analyzing, because if you are doing some pre-processing on the level of raw signals, it's gonna be good to extract the most like informative features and really get rid of noise before you do some sort of ERP analysis or time frequency analysis or even classification. I think pre-processing your data is very important because it's gonna maximize your signal to noise ratio and makes it easier to see an effect if it really exists in your data. So next we're gonna see manual cleaning. We're going to execute different blocks of manual cleaning and see how we can clean our data using lively vectors. Thank you so much for being patient and completing the video until this moment, and see you next time.